There are a couple of, we continue our lecture 10 here. There's a couple of quantities we need to call our attention to in the property tables. You can go look at them here. Um, Notice this K value, this little k, lowercase k value. Let's talk about what that is. That is the lowercase k value. I should have changed my ink back from black there. It's okay. Lowercase k, especially for ideal gases, is the ratio of C sub p to C sub v. We talked about last time that C sub p is always the larger quantity, because if we do have the oversimplified constant pressure scenario, kind of like we saw in the last problem, right, remember, if you've got a constant pressure scenario, then in order to increase the temperature, which means you're increasing the internal energy, the heat is also going to have to account for this boundary work occurring at constant pressure. So you end up with this M delta U plus the boundary work, which generates M delta H. So the C sub P describes the delta H quantity. So it's always going to be larger than the C sub V quantity. So K is always going to be greater than 1. The K value does vary as a function of temperature, but it's a little more stable than the C sub P and C sub V values. A K value of 1.4 is almost always true for air at just about any temperature. For ideal gases, there is a difference, a known constant difference between the values for C sub P and C sub V, and that is very simply the gas constant, the R value for your particular substance. So the C sub P and C sub V value will always be a value of R in between. All right, so that's kind of gives us the lowdown, the rules, and what I need to know about finding properties for an ideal gas. Use PV is equal to RT for describing how PV and T relate to each other. Use property tables or specific heats to find U and H as functions of temperature. And here's additional stuff to know. You probably won't need this too often again until about chapter 7, which in the summertime gets upon us a lot faster than we want it to, but that's just how it is. So that's for ideal gases. Now, for solids and liquids. And so if I'm dealing with a solid or a liquid, so that's kind of the third type of substance I might deal with. I've got water and R134 is the first category of substances. Ideal gases is the second category of substances. And then solids and liquids I would category together kind of as a third category of substances that I might encounter and I need to figure out properties for. So here's what we find is that the specific volume is going to be a function. If I've got a liquid staying a liquid or a solid staying a solid, those are the specific volume really isn't going to change much. If it does vary, it's going to be a function of mostly temperature. Right? So for the variation of specific volume and other properties being U, H, and S. These are going to be functions of temperature for the solid or liquid. So if I know the temperature, I should be able to describe either those properties or their changes. And what we find is the change in internal energy, for example. Well, let's do it on a differential basis first. Rather than delta U, let's start with a differential basis. So a change in internal energy is going to equal a specific heat times a change in temperature. Now, in your text, they like to use a letter P here on that specific heat. I wish they wouldn't, but they do. A lot of texts will just simply use a C value, a specific heat. But in your text, for solids and liquids, C sub P is going to relate delta U. What that means is that the change in internal energy is going to be approximated by C sub P at the average temperature times the change in temperature. That's if I happen to know, if I've got C sub P, if I can find C sub P at, apologize, at different values, right? Different temperature values, then I would just take the average temperature, find C sub P at the average temperature and multiply by the change in temperature. That gives me a very good, excuse me, I'm sorry, very good approximation for delta U. Okay. Now, it's very important that I'm going to add another if and only if here, I double F. Talked about an if and only if earlier in the previous video with the example. If and only if phase is constant. If the phase is not constant, basically what I'm doing here is I'm assuming that the specific heat up here is constant. I'm integrating specific heat with respect to temperature, and then I'm pulling that constant out of the integral, and I'm multiplying that by the integral of dt, which just becomes delta t, because the integral of du just becomes delta u. So I'm assuming this is constant. The specific heat is constant in order for this approximation to work. If the phase is not constant, if I've got solids that melt and transform into liquids, then that specific heat is no longer constant, and therefore this approximation does not work. Now, let's say I've got a really cold block of ice and I heat it up to a certain temperature until it starts melting. Well, then during that heat up process, the phase is constant and this works. Then during the melting process, there's going to be a different amount of energy transfer occur, energy change to occur. I'll have to compute using the latent heat of melting. I'll have to figure out how much mass is present, figure out how much energy is required to melt all of the ice into liquid. And then once I start heating the liquid up, now I've got a new C sub P for the liquid. And so again, to go from solid to liquid, I'm going to end up basically having to break it up into three parts. This would be the part. This would work just fine for the part where it's solid increasing temperature. And this will also work for the part where I've got liquid increasing temperature. But this does not describe the melting or the fusion process. Okay. So if the phase is constant, solid staying a solid, liquid staying a liquid, undergoing a temperature change, this allows us to compute the change in internal energy. Now, we just looked in the previous example, we said that, remember, for enthalpy by definition is the sum of U and the product of pressure times volume. Well, let's go to a differential basis. So if I take the derivative of this expression, that means dH is equal to du plus, then I've got to do a product rule here for PV. So product rule says it's going to be P dV plus V dP. Well, what we find is that for solids and liquids, again, for solids and liquids, the volume really doesn't change. The molecules are all packed together in both solid and liquid phase. The molecules are packed together. There's no space. So when I try to squeeze them, those molecules are already squeezed together. I can't really change the volume. So that quantity approximates or approximately goes to zero. So what I'm left with then is now I need to integrate. If I integrate both sides of this equation, where this guy goes to zero, well, I need to integrate dH from state 1 to 2. That becomes H2 minus H1. That's going to equal the integral of du. Well, that becomes delta U. And then I need to integrate VdP. Well, V is essentially constant. So I'm integrating dP. Well, that just becomes delta P. So this becomes V times the change in pressure. And remember, delta U, we've said for solids and liquids, I can approximate delta U as C sub P for solids and liquids at the average temperature times the change in temperature plus specific volume times the change in pressure. When I often teach fluid mechanics, this term, V delta P over here, this term often ends up being delta P over rho, which is the same thing. So if you've had fluid mechanics, you probably have seen in the Bernoulli equation, for example, delta P over rho. That's representing that quantity right there is what it is. Okay. Now, there's two main scenarios I'm going to deal with in this text is if I've got essentially a negligible or no major change in pressure. If I go back and look at this expression here, if there's no change in pressure, this second term goes away. Now, delta H can be approximated as C sub P for the particular solid or liquid at the average temperature times the change in temperature. And if I've got a no change in temperature, but then that means there's probably a change in pressure, then what I can do is I can describe this change in enthalpy as the specific volume times the change in pressure. This is the equation for what we call an ideal pump. A pump is a device that's going to increase the energy of a liquid stream. And often how that manifests, that increase in energy, that's delta H, ends up manifesting itself as an increase in the pressure of the fluid. And that's going to basically, you get a higher pressure at one point, and that's going to push then fluid further downstream to move out of its way downstream. Okay. One of those things you'll encounter that occasionally in this course. It's a little outside of what we're normally going to deal with. If I do need to know a change in enthalpy for some reason for a solid or a liquid, as long as the phase is constant, I can use C sub P at the average temperature times delta T to find that quantity as well. Okay. All right. Let's look at an example here. And we've got, actually, you know what? That's not the worst place to stop this video and start the next one. So that's what I'm going to do is I'm going to stop recording here and we'll go to the next video for this.